All right, this is the video covering section 3.1. It is all about vectors. So we're going to be doing vector operations. We looked at free fall. Free fall is important because now we're going to start applying vectors to situation when things that are falling or a block sliding down an inclined plane, maybe a Pokemon sliding down an inclined plane. I don't know. But let's get to it. All right, so a strategic approach. Chapter 3, vectors in end motion in two dimensions. Okay, so last time we looked at 1D. Now we're going to add in 2D. So things are going to be moving in a parabola. We're going to be launching projectiles. We're going to have X and Y. And for this class, we're not going to do any more dimensions than just two dimensions. Okay, anything more than that, it starts to get a little crazy. Also, you can always adjust your coordinate system, right? We haven't talked a lot about our coordinate system, but it's important to remember that you can move your coordinate system. You can say x equals 0 here or y equals 0 here. If that helps you solve the problem, then you can do that, okay? So we're going to use vector addition, okay? So go ahead and I'm gonna click on that app right now. We're just gonna get it out, man. Get your 2D vector addition out because we're gonna use this a lot. Okay, so basically anytime in this video that we need to do a vector, I'm gonna get out this little vector video game. It's amazing. Okay. I love these PhET simulations. Click on the PhET simulation. These are totally great. Okay, this was done. This was NSF funded. And these things are awesome, right? I mean, it's basically a physics video game. What could be better? I want this big. Okay, so I'm gonna show my thumb here. Okay, that's fine. All right, so we're gonna get that out, and we're gonna do a lot of our vector addition with that simulation. Okay, so just know that. All right, chapter goal. Learn more about vectors and my head is too big. And to use vectors as a tool to analyze motion in two dimensions. Okay, so Mr. Cheetah here, he jumps through the air. Whoosh. Wait, that's not a very, I don't like that. I need a thicker line, Mr. Cheetah. This is not good. Mr. Cheetah, how do I make my line's bigger? I know there was a place to click. Oh, there it is. Okay. I don't want that one. Yeah, no. I apologize. Technical details. Sorry about that. Okay, we're gonna go back here. I'm gonna make a big arrow. I like big fat arrows. Okay, Mr. Cheetah jumps up in the air. Whoosh. Okay, there he is. Now, in this one, okay, Mr. Cheetah, and it's still I want it fatter. All right, big arrow. Okay, Mr. Cheetah, he's gonna go here, and this is gonna be my X component of the vector. And then this is going to be my y component of the vector. Okay, so I'm going to redraw this vector here. I want it darker. Okay, so this is my vector. And that is really hard to see. Oh my goodness. What color could I use? Blue, white. Yeah, I guess we'll do purple. There we go. Okay, purple. Maybe it's yeah, purple is okay. Well, I don't know if anyone's colorblind, but all right. So I've got my X component and my Y component, and this is going to be really important in projectile motion problem because those two different motions are separate. Okay, we need to treat X and Y motion separate. The thing about X motion is Mr. Cheetah will continue forward at the same velocity Because there's no forces acting on him besides wind resistance, but we're going to ignore that, okay? Now, y, on the other hand, gravity is acting on y, and so his y velocity is going to change a lot. So that's the important thing to remember about x and y. We treat them separate. We do x and y separately, and we can solve problems that way. Okay, so here, these guys are playing basketball. He shoots the basketball, and the velocity from the ball is pointed in this direction. That's just the direction of the velocity. And it's got two components, x and y. X doesn't change. X is the same all the way over here, does not change. Y, on the other hand, does change. And we're going to treat those separately. A leaping fish has a parabolic arc. I'm going to put my computer over here. I have to go at an angle. I wish it would stop. Okay, there we go. Perfect. Okay. So, uh, he has a parabolic arc. It's an example of projectile motion. The details are the same for the fish and the basketball. It doesn't matter. Fish and basketball are the same. Okay, the riders move in a circle at a constant speed, but they have an acceleration because the direction is constantly changing. Okay, you can either accelerate because your velocity vector is the magnitude is changing or the direction is changing. Okay. Um, so we'll learn how to find the magnitude of our velocity. Okay, so here, chapter 3, looking back, free fall. So we learned in 2.7 that an object talks straight up. Hey, the acceleration is the same whether the object is coming up or it's going down. It's the same. Okay. A doesn't change. Doesn't matter what direction the velocity is. A doesn't change. Okay, here's the question. A player kicks a soccer ball straight up into the air. The ball takes 2 seconds to reach the highest point. Approximately how fast was the ball moving when it left the player's foot? Okay, the ball takes 2 seconds to reach its highest point. Okay, so we have time. Okay, um, and we have acceleration. Okay, so I think you're supposed to do this in your head, but I'm gonna use paper. Okay. You can do it in your head. That's fine. I'm gonna use paper, and my camera's not connected. No. Well, I don't want the answer. Okay, there we go. All right, so we're gonna figure it out. Figure it out, man. All right. There's my yeah. All right. So now it tells us that it takes 2 seconds to reach the top, so we've got time. Okay, so t equals 2.0 seconds. I could change the window. There, we got some light. Okay. What did I write here? 2.0 seconds to reach the top. Okay. So I know that I'm gonna probably use this equation. Y final equals Y initial. And what I want to know is I want to know what's my initial velocity. So this will be VI times T minus 1/2 AT squared. So what could I do? I don't know what the highest point is. Okay. Um, how fast was the ball moving when it left the player's foot? Hmm. Reach its highest point. Oh, how could we solve this one? Okay. Well, let's put in some numbers here. Okay, so I don't know what YF is, so that's kind of a problem, but let's just go with that. Y initial 0, and then I want to know what VI times T is. Okay, so this will be 2. I don't know what Y is. So what equations could I use for this one? Okay. Um, oh, so they gave us the time, but do we need to know what the time is? Okay, actually, maybe we don't. I don't like this one. It's not going anywhere because there's two unknowns, and then I'd need two equations, but maybe I'm just gonna ignore the time. Okay, so V No, because I can't use that one. That doesn't give me time either. What could I do? Well, the other thing is, okay, we have, we're gonna have to use multiple equations. How could we solve this one? Okay, there's v squared f equals vi squared. Okay, and then this will be plus or minus 2g times delta x. Okay, so that's one equation. And we can say, oh, I know what we'll do. All right. So we also have VF equals AT, right? That's one equation. We can put that in there, or GT, right? This is true. Oh, so our, oh, and, what am I doing here? Yeah. Okay, so our final velocity is equal to 0. And we should have delta F equals G times delta T. Okay. So and I need to know my initial velocity. And then this was minus 9.8. Okay. 9.8 meters per second. Oh, maybe this is it. Okay. So, oh yeah. How fast was, yeah, this is it right here. Okay. So we know everything. We have V equals G times T. What am I doing? Okay. So this was 2.0 seconds. Okay. Um, yeah, I think this was all we needed. Okay, so and this should be a negative here because we wanted to come out positive. Okay, so this was VI equals basically 20 meters per second because we had 10 times 2, and indeed the answer is 20 meters per second. Oh, okay, so we just use this equation right here. Let's draw it over here, what we did. All right, so we have VF minus VI, okay, equals minus 9.8 times t, or time, which was or yeah, we'll just say t. So times t, okay, and v final is 0. That just goes to 0. So now we have v initial. The minus signs cancel, and so we get vi equals 9.8 times t. We know what t is. That's 2. So we got the answer. All right. Well, that shouldn't have been that hard for me. But you know what? See, that's okay because it doesn't matter even if you've done these problems before, okay? They're not necessarily easy. You still have to think about it. So even if you don't get it the first time, that's okay. Not it Most people don't, right? I never got it the first time. I was always slow at physics problems. I mean, I figured it out eventually, but I wasn't the quickest. That is definitely true. I was not the quickest ever. Okay. But let's go on here. All right, the blank of a vector is always a positive quantity. Okay, well, let's look at the first. The x component and the y component. No, those could be negative because they could be pointing to the left or down. Okay, magnitude. Now, magnitude is the length of the vector. Okay, so that one I don't think can be negative. The direction definitely can be negative. It can point in literally any direction. So magnitude, it's C. The answer is C because it's always the length of the vector is always positive, and it's always, yeah, it can't be negative. You can't have a negative length. All right. Because if a vector is negative, that just tells you what direction it's pointing in. All right, let's look at this one. AX is positive if AX, the vector, is directed blank, and AY is positive if AY vector is directed blank. Okay, well, in our coordinate system, we always say that in the X direction, the right is positive, and also in the Y direction, okay, up is positive. All right, so let me draw a picture of that because, yep, okay. So here we're going to draw a coordinate system, okay, and what we are going to do, okay, our coordinate system, this is the convention that we're going to use. So here's our axis, okay, this is y, and this way is x. Okay, so I've got, yeah, here's my axis, and I've got x and y. Okay, so this way is X, it's in meters, and this way is Y, it's also in meters. Okay, so we say that this way to the right is positive, right? Is positive. Okay, and up is also positive. Okay, that's always true. And then down is negative and left is negative. Okay, this is the standard convention that we use, and so we're gonna go with this. From here on out, right is positive and left is negative. It doesn't have to be. I mean, you could do whatever you want as long as you're consistent. Okay. So like my right hand is not positive, okay, but it's just in this coordinate system. Okay, then it is that way. Okay, but you're like, well, what if I turn over my page? What if I turn over my page? Now positive is pointing the other way. Oh no. So if you just look at the other side, it's flipped, right? So it's totally relative, but it doesn't matter. Okay, well, anyways. All right, so let's move on. Let's move on. We're making a quick video here. Just a quick intro to three, which is vectors. We did this one, but oh wait, we didn't say which one, but it was, yeah, right. It's probably okay. Acceleration of a car rolling down a ramp depends on what? The angle of the ramp. The length of the ramp. Both the angle of the ramp and the length of the ramp. Neither the angle of the ramp or the length of the ramp. Okay, well, I know this because I've moved before and I tried to push a cart up a ramp. Or maybe have you ever had your car stop and you try and push it uphill? It's hard. There's more force pushing against you. In fact, you don't want to try and push a car up a hill because it'll roll back on you. Okay. So the length of the ramp, if it's really if the length isn't going to do anything, that's not going to change gravity. But the angle can change can change the length or can change the acceleration that you experience. That makes sense because the steeper the hill the faster you're going to go down it, and you're going to accelerate much quicker if the angle is steeper. Okay, so the correct answer is A, the angle of the ramp. But let's drill down on this one a little bit. Okay, and I'm going to draw a picture here, and let's draw a ramp. Okay, so we're going to draw a ramp here. Okay, now here's how this kind of works. Okay, let's say we have Dr. Wisby on a skateboard. Okay, yes, I like to ride my skateboard, and I don't do it that often, but when I'm in physics class, I like to ride my skateboard. So I'll put some videos of me skateboarding on Discord. I usually get up on a desk and skateboard in the classroom, so you're really missing out because you didn't get to see me skateboard on a desk. But I have videos of me skateboarding down the parking garage at SLU. Okay, so here's my angle. Okay, it's some angle theta. Now, gravity is acting on me from my center of mass, and it is pulling me downwards. And the force due to gravity is m times g. Okay, that's a force. Or my acceleration, okay, it's g. Okay, and it's pointed downwards. Okay, now there is an angle here, okay, and that angle is really important, okay, because if I now draw an angle perpendicular to this, okay, so this is going to be perpendicular means at a 90-degree angle, okay, I'm going to draw this line. This is perpendicular to the surface, okay, and then I draw another line over here, okay, then this purple line here, G is the hypotenuse of a triangle, okay, so here's where our trig is going to come in. So we're going to use some trig here now, okay? Because I know that if the hill isn't very steep here, I'm not going to go super fast, right? I go up on the parking garage and at the top of uh, McDonnell Douglas Hall, it's not very steep, so I don't go that super fast, right? If it was straight down, that is just free fall, and then you like fall straight down. Okay. So actually, I'm going to show you the video now. So let's watch this video of me skating down the parking garage. We're gonna go this way. We're gonna travel diagonally, and it's a little steep to just go straight down, but um, yeah, we're gonna go for it. Okay, so let's go an angle here, and oh yeah, this is pretty nice, right? So I'm traveling at a constant velocity, guys. Wow, I have achieved constant momentum. Oh, we got to turn. It's going a little too fast. Oh, there we go. Yes, gaining a little momentum. That's okay. Oh, now we're doing the slingshot effect. Go down the parking garage again, but no, no, it wasn't. Okay, so that was me riding down the top of the parking garage. Oh, okay. So it's going down the parking garage, and um, only a component of the gravity was pulling me down. And actually, the force due to gravity was actually less than the force of friction. So you actually don't end up going that fast unless it's really steep. And so how does it work? Well, G pulls us down this way. Okay, that's the hypotenuse of our triangle. So if we turn it around now, okay, now we've got a right triangle here. Okay. And we want this component because, see, this component is pointing down the hill. Okay. So to get the opposite side here, and here's something about math that you need to know. Okay. This angle right here is the same as this angle of my triangle. So theta. Okay, so that's going to be theta. Okay, that angle is the same as this angle. It just is. Just accept it. All right, you could prove it to yourself later. I'm not going to do that. Okay, so this is the opposite side of our triangle. Okay, so that would mean that it is. Okay, so we're going to write this down now. Okay, our hypotenuse, right? We're getting the opposite side. Okay, and this is going to be the acceleration in x. So we'll call it ax because see, we're saying that positive x now is pointing down the hill. That's positive x. This is going to be our acceleration, ax, and it's the opposite side of this triangle. And this is really important, okay? So it's going to be g times sine of theta, okay? So the smaller the angle is, that gets closer to zero, so this goes to zero. So if it is zero, then there's no acceleration because you're on a flat surface. Okay. The steeper this gets, if it gets 90 degrees, which means you're falling off of a cliff, okay, that's a maximum. So it's going to be somewhere in between here. Okay. And so that is my acceleration pulling me down on the skateboard. Okay. So that my acceleration then is going to be A times G sine of theta. And you should probably write this down on your card. Make this diagram, okay? We're going to use this for the problems in chapter 3. But we're going to use this a lot, okay? So this is very common, and this is the component of the vector. Okay, so G is a vector. That's the force of gravity. It is a vector. Okay, so we're saying that my acceleration here, I'm going to put a little hat on it. There's a little arrow pointing to the right because it's a vector. It's going down. Okay, this is the component here of this one. Okay, so this diagram is really important, and you understand this, and we'll use it again. We're going to come back to this a lot. Okay, yeah, I gave myself a shirt, basically. There we go. Okay, so that's me on a skateboard, my little frisbee. Okay. All right, let's go back and see what we got here in this one. And we're just doing a little part of this. Okay, so here's another question. Let's do this one. Acceleration vector of a particle in projectile motion points along the path of the particle. Now you should really read the chapter before you try and answer these, okay? So I would go through the chapter, look at the PowerPoint slides, watch these videos, but read the chapter. Acceleration vector of a particle, projectile motion does what? Does it point along the path of the particle? I don't know. Does gravity change directions? If gravity doesn't, then no. Okay, is directed horizontally. No, I don't think gravity goes parallel to the surface. It goes perpendicularly. Vanishes at the highest point. No, acceleration never vanishes. It's always constant. D is directed down at all times. Yes, the answer is D emphatically. G always points down. Okay. Now, if you have an angle here, there's a component of it that will act down this way, and then, um, but gravity is still directed down all the time. I'm probably going to ask that on the test. Okay. The acceleration of a vector of a particle in uniform circular motion points tangent to the circle in the direction of motion, points tangent to the circle opposite the direction of motion, or zero. I don't think it's zero. That's no. Points towards the center of the circle or points outward from the center of the circle. Oh, we're going to have to talk about this one. Okay, you're going to have to go back and think about being on a merry-go-round. What direction were you accelerating? Good thing that my room is full of physics experiments here, and other people, when they come into my house and they look at my office, they're like, what is all this crap lying around? I'm like, it's physics. Hey, this is not crap. So I said the C word. I'm sorry, guys. Okay, so, oh, geez. Try not to destroy. Oh, try not to destroy anything. Okay. So, swinging this thing around. It's going in a circle. Which way is the acceleration pointing? I'm trying not to hit myself in the head. Okay. So it's going in a circle. Okay. Hey, this thing's going in a circle. Or, yeah, halfway in a circle. Okay. Maybe over my. No, this is dangerous. Oh gosh. Okay. I don't have a lot of space in my office here. I don't want to put a hole through the wall. This could easily go through the wall. Okay, we'll save that for the catapult chapter. I don't think there's a catapult chapter, but we'll talk about catapults. Okay. So, which way is the acceleration going? I want you to think about it. I'll tell you in the next video. We're going to talk about that one. Oh, yeah, that's good. We'll come back to that one, okay? But I want you to think about it. When you're on a merry-go-round, which way are you accelerating? Are you accelerating towards the circle? Towards the center of the circle? Are you pulled inwards? Are you pulled outwards? You fly away from it? Or is it something else? Something more sinister? No, not sinister. Okay. All right. Let's go on. Clicking on the screen, but here's the slide. Okay, I gotta share my screen. All right, using vectors. We're gonna use vectors. Absolutely. Okay, a vector is a quantity with both size, magnitude, and direction. The magnitude is the length of the arrow, and then the direction could be the angle here. So if it's if it's from the horizontal axis, okay, so maybe here's your x-axis, okay, then that's your angle, okay. So there's a direction and a magnitude. They have both, okay. The magnitude of the vector is represented by a letter without an arrow, okay. Uh, in this case, the particle speed, the magnitude of the velocity vector, v, and then see they'll put this little arrow over that. That means it's a vector. And its magnitude v without the arrow is 5 meters per second. Magnitude of a vector of a scalar, the magnitude of a vector, a scalar quantity, cannot be negative. It's always positive. Okay. And some things in this universe are scalars, and some things are vectors. Velocity is a vector, but oranges are a scalar, right? I don't have, unless you throw your oranges. But the number of oranges, or maybe a bag of onions. I have a bag of onions, and I had 2 onions in my bag of onions. That's a scalar quantity. My bag of onions does not have a direction. You see what I'm saying? The units are onions. And so if I said, what's 2 bananas plus 2 onions? The answer is not 4 apples, right? The units are important. And onions are always onions. Just remember that. If you don't remember anything else from this class, well, hopefully you remember F equals MA. But onions are onions, and you can't add them to apples and get bananas. They're scalars. They don't have a direction unless you throw them. Then the onion would have a velocity and a direction. But the onion itself is not a vector, it is a scalar. Okay. Displacement vector is a straight line connected from the initial position to the final position, regardless of the action. Okay, well, you know what? Before we go any further, I'm going to actually end this video because I think I need to make sure my son is getting into bed. So this is, I guess it's another pre-chapter 3 video, but we need to do some vectors. Okay. So what about what vectors are and what we're going to do with them. So thanks for watching this video, and tune in for the next one. We're going to do a bunch of vector math. Thank you, Bulbasaur.